Well, good morning or good afternoon, everyone, depending on your time zone. It's morning back here on the West Coast. I'm Carl Pilcher, and I am going to introduce our speaker today for the NAI Director Seminar. Our speaker is Drake Deming from Goddard Space Flight Center, a member of the Goddard Space Flight Center team. I've known Drake for a lot of years, and I'm really glad that he was able to give this talk because there have been some very exciting recent results, particularly based on the Spitzer spacecraft data. And Drake is also going to tell us about how those kinds of results might be extrapolated to what would be possible with JWST. Drake received his PhD in astronomy in 1976 from the University of Illinois at Champaign-Urbana, and spent some time at the astronomy department at the University of Maryland, came to Goddard in 1979, and he has been there ever since, working on infrared observations of solar system objects. And obviously he's expanded his purview to observations of planetary objects in other solar systems. So today Drake's going to tell us about infrared spectra of extrasolar planets, and I will turn it over without further ado to Drake.
Okay. Thank you, Carl. First, I want to acknowledge my collaborators in this work. Jeremy Richardson was a NASA postdoctoral fellow at Goddard, and actually I wasn't his advisor. Jeremy worked in a couple of different laboratories, and his advisor was Bill Danchi over in the Exoplanet and Stellar Astrophysics Laboratory. Karen Horning is an undergraduate student at Florida Institute of Technology, and she was our summer astrobiology intern last summer, and Karen did a lot of the really hard work that's going to make the analysis that I'm going to show you today possible. Sarah Seeger is our team theorist, and in the early stages of this work she was at the Carnegie node, and she's since moved to MIT. And Joe Harrington is our collaborator at the University of Central Florida. And this talk is really divided into a series of topics. First, since I'm talking about spectra of extrasolar planets, I'm going to just review that very briefly, the status of that field. The known extrasolar planets extend from hot Jupiters to, in one or two cases, some planets that could be arguably called hot Earths. And I'll mention the possible detection of biomarkers. I'm not going to show you any actual biomarkers. These are just our future goal. But I'll try to relate the spectra that I'm going to show you for hot Jupiters to the eventual detection of biomarkers. Now, in order to show you that we've measured spectra of two extrasolar planets, I first have to show you that we can detect photons from extrasolar planets at all. So I'll briefly describe the first Spitzer detections and follow-up detections using Spitzer, using photometry to just measure the planets in a photometric mode. And then I'll talk about measuring the spectra of giant planets with Spitzer. I'll show you two extrasolar planets, spectra of two extrasolar planets, one measured by our group and another by another group that we worked in parallel with. And I'll finish up by saying how this might eventually lead to the spectra of what we call hot Earths, or close-in extrasolar terrestrial planets. Okay, well, since 1995, the Doppler groups have detected the bulk of the extrasolar planets. And the way to remind you how this works is the Doppler groups will look at a stellar system, and they won't detect the planet directly. That is, they won't see photons from the planet, but they'll see the Doppler reflex of the parent star as it orbits the center of mass of its planetary system. One of the earliest surprises of the results from this group was, in fact, the very first planet that was detected was orbiting the star 51 Pegasus, and it was a giant planet of nearly Jupiter mass, and it was in very close, 0.05 AU. That's 20 times closer to the to its star than the Earth is to the Sun. And these planets have been called by various names. I prefer to call them hot Jupiters because they're of Jupiter mass, but they're in close to the star. And in that close to the star, they're going to be very strongly irradiated on one side, as envisioned here by Greg Laughlin and James Cho, by stellar irradiation, where they're going to be heated to very high temperatures. Now, of course, ultimately, what we want to do in the field of astrobiology as concerns extrasolar planets is we would like to measure the spectrum of an Earth-like planet, or something at least close to an Earth-like planet being in the habitable zone. And this is some material from Vicky Meadows showing modeled spectra of Earth-like planets, where you could see an ozone signature near 9.5 microns, methane near 7.8 microns, possibly CO2 at 15 microns. And to measure these spectra, the technologically difficult but conceptually the most straightforward way would be to make a highly spatially resolved image of a star containing a planet, and then to isolate the planet and observe it with some very advanced space mission. And if you can separate stellar and planetary photons by some high technology method like this, then you can just take these planetary photons, you can put them through your spectrograph, and you have a spectrum. And it's a simple proposition. But technologically, this is very difficult, and it will be very expensive, and it hasn't been done yet. But for those of us who are interested in seeing this done, we can't wait. So we're pursuing other techniques, and those other techniques will use transits. Since many of these planets are close into their star, a close-in planet has a high probability to transit its star, that is, to cross in front of its star as seen from the Earth. The transit probability, if you calculate it, is the radius of the star divided by the orbital radius of the planet. And for the close-in hot Jupiter-type planets, that's about 10%. And early on in the history of this field, when there are about a dozen such planets known or in close from the Doppler surveys, statistically one of them should transit, and that one that was discovered to transit was HD 209458b, and this is Hubble observations of the transit of that, made from space, very high quality, very low noise photometry. The transit depth, the amount of light that the planet blocks, is about 1.5%, 1.6%. There are now 14 of these known transiting bright solar-type stars. And of course, the transit is very interesting. The depth of this transit tells us the amount of stellar light that the planet blocks, but we're not detecting light from the planet this way. In order to detect light from the planet, we have to use what's called the secondary eclipse. The transit is the primary eclipse, planet passing in front of the star. That tells us the size of the planet. And in principle, we can see, and in fact it has been done, radiation from the star transmitted through the planet's atmosphere. So in fact, the first detection of an atmosphere was made this way. But we can't see photons emitted by the planet. In order to do that, we have to go to the secondary eclipse. When the planet passes behind the star, then if we look in the combined light of the system, with no attempt to spatially resolve the system, we will see thermal radiation from the planet disappear and reappear. And in so doing, we'll learn particular about the atmosphere of that planet, because that thermal radiation that we receive emerges ultimately from the atmosphere of the planet. We'll also learn about its orbit and other things. But I'm going to focus here mainly on the spectra of two of these planets, which tell us about their atmosphere. Here are the first detections of photons from extrasolar planets. They were made with the Spitzer Space Telescope almost exactly 2 years ago this month. And they were, in fact, done. One of the great coincidences of astronomy is that the two detection papers were submitted on the same day to different journals, completely uncoordinated. The two groups had were not coordinating their measurements. Our group detected HD 209458b using Spitzer at 24 microns. This shows the secondary eclipse, where the light from the planet goes away, and then the radiation comes back again after eclipse. And then a group led by Dave Charbonneau at Harvard detected the planet called Trace 1 at 8 microns, and they also detected it at 4.5 microns, which isn't shown here. Now, the eclipse depth of the secondary eclipse is just the depth of it's the projected area ratio. This is really just the depth of the transit. And in the Rayleigh-Jeans limit, there's an additional factor, which is the ratio of temperatures. And this is something like 1/5 or 1/4. So these secondary eclipses are less deep than the transits, and that's why they're, of course, much noisier than transits. And these initial detections were, you can see that the data have a fair amount of scatter. An individual point wouldn't really be sufficient to detect these eclipses, but in aggregate, each of these eclipses is about a 6 sigma detection. And the temperature is about 1100 Kelvin. Now, although these were sort of two independent groups, and they both got about the same result on two different planets using different Spitzer instruments. Nevertheless, if you were a really skeptical person, you might say, well, 6 sigma, maybe I don't really believe that. Well, I will, in that case, I welcome that skepticism. I will show you an additional follow-up detection because later in 2005, an additional planet was detected that has an even greater transit depth and an even greater secondary eclipse depth due to the fact that the star that it orbits is much smaller, so the ratio of planetary flux to stellar flux is much better, and that's HD 189733b, and here's its secondary eclipse observed by Spitzer. Although, maybe you could be skeptical of the first detections. No one's going to be skeptical of this one. This is a 32 sigma detection of this planet at 16 microns. And this is the unbinned, the original Spitzer measurements, all of them every 10 seconds, and this is a binned plot just to show it more clearly. Again, the eclipse depth is the ratio of the projected area of the planet to star times the temperature ratio. And what I wanted to point out with this is that as you go down the main sequence to smaller stars, this is a K star. If you go to even smaller stars, if you go to M dwarf stars, this becomes an even more favorable situation in the infrared. And the reason is that this area ratio is the dominant term, whereas this term is the temperatures of the planets and the stars don't vary all that much. The temperature of the planet is the temperature of the star in thermal equilibrium times the angular diameter of the star as seen from the planet and the square root of that. So this varies relatively mildly, whereas this term varies predominantly. And as you go to smaller stars, this becomes more favorable. So lower main sequence stars are very good for high signal-to-noise planet detection using secondary eclipses. So I think by this I've convinced you that we're seeing photons from extrasolar giant planets. So now I want to talk about dissecting those photons and looking at their spectra. The previous detections were photometric. And now when we begin dividing the photons into smaller wavelength bins, it's a more challenging problem. But nevertheless, there are two transiting planets, HD 189733 that I just showed you, and HD 209458, which are bright enough that we can measure their spectra using the relatively modest aperture. Spitzer's an 85 centimeter telescope. And both of those detections were published earlier this year. Our detection was in Nature. There's a group headed by Carl Grillmair at IPAC, at the Spitzer Science Center, and Dave Charbonneau collaborated with him, who detected HD 189733, and I'll show you their results also. There's another analysis done by Mark Swain, who reanalyzed our data, and I won't discuss Mark's result unless someone asks. Here's the principle that we use. And I emphasize this is the principle. This is not what we actually do, but this is the conceptual basis of what we do. Before the secondary eclipse, we use Spitzer to measure the combined light, the spectrum of the star plus planet. Now we know when the planet is going to be in eclipse, so during that time we observe the stellar spectrum. Spitzer's in a very stable heliocentric orbit. The instrument doesn't change very much, and so we can subtract the two and derive the planet's spectrum. So it's a very simple idea. In practice, it gets more complicated, and I'm going to show you some of the actual, nitty-gritty, dirty laundry of how we do this analysis. Here's an actual imaging frame from Spitzer, and I'm tempted to say this is raw data, but the Spitzer people would correct me. This is what they call BCD, or Basic Calibrated Data. It's an image of the spectrum of HD 209458b. Here's the we observed between about 7.5 microns to about 14 microns. Here, this bright streak, is the spectrum of the star plus the planet. And you can see all the bad pixels on the array, the hot pixels. Over at the right side of the detector array, there are what are called the peak-up arrays, which are just regions which receive, which are not dispersed. So the star, first the telescope places the star here to center it, and then offsets it to the slit of the spectrograph. We actually can use the peak-up arrays for various things. They're very bright here because they're not seeing dispersed light. They're looking at the background radiation from our zodiacal background directly. But we actually observed 2 full eclipses of this planet. Each eclipse was a 6-hour sequence of observations. Each one of which is like this. These were made in July 2005. Shortly after we did the photometric detections, we immediately jumped on this spectroscopic technique. Our observations are basically 60-second exposures. There are 280 of them per eclipse, and we have 2 eclipses, so we have a total of 560 data frames that look like this. There is a telescope nod at the center of the eclipse. We move the spectrum so that we can subtract the background and what's under the spectrum more accurately. The spectral resolving power is about 100, and that's just sort of barely what a spectroscopist would call a spectrum. But it is a legitimate, that's a high enough spectral resolution. It's not photometry, it's spectroscopy. Now we can immediately estimate what signal to noise we expect on the planet in combined light. The signal to noise on this spectrum, star plus planet, is about 100 in a given pixel, a pixel meaning a given wavelength, per spectrum. Since we have 560 spectra, about half of which are in eclipse and half of which are out of eclipse, to detect the spectrum of the planet, we have to basically at each wavelength define 2 levels, an in-eclipse level and an out-of-eclipse level. Each level is defined by, there are 560 total spectra, each level is defined by half of those, or about 280, so the signal to noise on each level improves by 100 times the square root of 280. But then since we have to compare 2 independent levels, we lose the square root of 2. And if you work that out, in our combined data at each wavelength, we would have a signal to noise on the combined system of about 1200 on star plus planet. The planet is about 0.3% of this total. Therefore, our signal to noise on the planet at a given wavelength will be about 4, which is low signal to noise. We are limited by the number of photons that Spitzer can detect. Now, in order to get to that photon limit, we have to deal with some instrument and telescope uncertainties, some systematic effects. There are 2 principal systematic effects. First of all, there's something we call the ramp. And what happens is when you first put light on the spectra, on the detector in the infrared spectrograph, and also on some of the other Spitzer detectors, see the same effect. The intensity that comes out of the detector, even though the source isn't changing, the intensity gradually ramps up with time and asymptotically approaches some constant value over many hours. And this is recently, the physical cause of this has recently been identified by the IRAC group at the Center for Astrophysics. And they believe this is due to charge trapping in the detector material. The first photons that come in don't produce electrons. Instead, the electrons that get freed from the detector get trapped by ionized impurities in the detector, and you don't really reach full sensitivity until you fill all those charge traps, and that makes for this ramping up baseline. So we have to deal with this. We have to subtract this from our data. The other effect is there's a telescope oscillation, and we're taking spectra. The Spitzer telescope is wonderful, but it has a 0.05 arcsecond oscillation in position with a period of about 1 hour. And because the telescope is oscillating, that means the star is moving on the slit, and the amount of light that comes through our slit is oscillating by several percent due to that telescope oscillation. Well, you can imagine if we didn't subtract this, we're looking for the spectra of a planet, which is a few tenths of a percent. This oscillation is an order of magnitude larger than the planet signal. Fortunately, where the telescope is pointed is not a function of wavelength. So the phase of this oscillation is absolutely independent of wavelength. Its amplitude is slightly dependent on wavelength, but we can nevertheless subtract it. To show you that we do see the planet at all, I've simply summed all of the wavelengths over time. And you can see here's the total intensity in our spectra as a function, and this is both eclipses averaged together. And you can see the ramp. See how it rises up and then approaches some asymptotic value. These dotted lines are where ingress and egress of the planet's eclipse occur. And you can see there is a decrease at this time, and that's the eclipse of the planet. You can also see the residual oscillation. Since we've averaged two independent eclipses, the oscillation's not as big because the oscillation had a different phase, because those eclipses were measured a week apart. The telescope repointed to completely reset the phase of the oscillation. So it tends to average out here. But what we do is we independently subtract it in each eclipse. But I average these together because I have to show you, first of all, that we do see the eclipse of the planet. Now, here's how we actually get the spectra. It's a multi-step process. The first thing we have to do is we have images of the spectra. We have to actually get spectra. That means we have to remove all those bad pixels, we have to subtract the background, and we have to sum over a spatial window. And we actually spent about 3 months doing this, and we did it 3 different ways. We had 2 sort of custom ways to do it, where we would look at the actual time dependence of the intensity in each pixel, and we would throw away bad pixels. We literally, every pixel in the detector had to become our personal friend. And we had two members of our team do this with their own custom procedures. Then there's standard software to do it by the Spitzer method, and we did that too. And then we took all those results and put them through our entire analysis to get the spectrum of the planet. And we can't just pick the method we like the best. We have to have some objective way of doing it. And the objective method that we decided to pick the best method was we would compare the planet's spectrum on the 2 eclipses, and we would do a chi-squared of the difference between the 2 eclipses from the planet's spectrum. And the method that produced the minimum chi-squared is the method we used. It turned out to be one of our custom extraction methods, which isn't surprising because the characteristics of the detector do change with time. So if we use something customized for our own data, that's going to produce the best results. Then what we do is we really don't subtract spectra. We really treat these spectra as a series of photometry measurements. In other words, we normalize the intensities at each wavelength to an average value of unity. Another way of saying that is we divide every spectrum by the average spectrum of the star. And that normalizes the intensity at each wavelength to unity, and it puts our final results in what's called contrast units, the ratio of the planet to the star. We then give up the average eclipse. And in other words, we subtract the average time series. And when we do that, this average eclipse goes away. We subtract it out of the data. What we're left with are the differences in that eclipse from one wavelength to the next. So if the planet's spectrum were constant over our wavelength range, we would see nothing. But because we do see the average eclipse, we would know that we are detecting the flux from the planet, but that it's constant with wavelength. Now, the advantage of subtracting that average time series is it removes most of the systematics. It removes the intensity ramp apart from a linear term, and it very effectively removes the telescope oscillation. We then, to each time series, we fit an eclipse curve. And we do allow that eclipse curve to have a linear baseline, a sloping up or down at each wavelength. And we derive the planet's spectrum from the amplitude of those eclipse curves. Those are differential eclipses. Let's say that the planet is brighter at one wavelength than it is at another. Then when we subtract the average time series, we will have a little bit of residual extra eclipse at that wavelength where the planet is brighter. And thus our eclipse, our method of fitting the eclipse curve will detect that little extra eclipse, and we will take that extra eclipse depth and translate it into an extra depth for an extra brightness for the planet. We then go through and reject any wavelengths that have poor fits. If this fit to the eclipse curve doesn't show the correct ingress time, the correct egress time, the correct central phase, we throw it away. And about 5% of the wavelengths have residual ramp effects, so the systematics are not effectively removed, or those pixels are very poorly behaved. We throw those away. We then compare 2 independent eclipses. And this is an example of a differential eclipse. This is the point where we find the brightest peak in the planet's spectrum. And this is a differential eclipse. It's centered at phase 0.5, where it's supposed to. This dashed line is a theoretical eclipse curve that has the correct ingress time and egress time and the correct central phase. We don't shift this back and forth. All we do is we fit its amplitude. We stretch it up and down. Here are the aggregate results for 2 eclipses of this planet. 0 is right here. So you can see we're detecting, at the longest wavelengths, we basically we barely detect the planet's continuum. We can't really say anything about any structure. There are 2 features in this spectrum that we regard as real, in the sense that although there are only 3 or 4 sigma detections, and we would like not to be in the 3 or 4 sigma domain, but that's the amount of photons we have. But these features have passed at least all of our tests. And actually, there's another aspect that I'll talk about that's even more robust. But the 2 peaks, near about 9.5 microns, we see this kind of broad peak in the spectrum. And you notice that the blue points and the red points both show it. These are 2 independent eclipses. This is the stretching resonance between silicon and oxygen. There are many, many astrophysical sources, not extrasolar planets, but protoplanetary objects and disks and so forth, which show silicate emission at this wavelength. And so this is a very familiar feature to astronomers. We think that this is indicative of silicate clouds in the atmosphere of the planet. There is another sharper feature in the spectrum that passes our tests to be real. In fact, that differential eclipse that I showed you, this eclipse is made at the peak of that narrow feature. And initially, this is at 7.78 microns, and initially we thought this was the Q branch of methane that was showing an emission because the planet had a hot stratosphere. We've since been able to determine that its wavelength is not coincident with the Q branch. The Q branch is at like 7.65 microns, and it shifts to longer wavelengths at hotter temperatures, but not enough. And we very carefully checked the wavelength calibration, and we talked to the folks at the Spitzer Science Center, and they tell us that the wavelength calibration of Spitzer, it's out of the question for it to be off by, it would have to be off by like 2 pixels. So this feature can't be methane. About the only thing that we can't eliminate, we don't know what it is, but we can't eliminate that it's due to some feature due to there's a carbon-carbon stretching resonance near about 7.8 microns. And in most astrophysical sources, this is seen in polycyclic aromatic hydrocarbons, PAH. The PAH has another emission feature at 11.3 microns, which we don't see anything there. But the reason we can't eliminate this as being PAH is that other resonance weakens in high radiation environments. And we're in 0.05 AU from a relatively hot star, certainly a high radiation environment. So it's possible that we're only seeing this CC stretch. There is another carbon-carbon stretch at 6.2 microns, and we have proposed that Spitzer observe at shorter wavelengths. So we won't really conclude anything about this until we can look at the wavelength of that other resonance. Now, this lower panel shows you the average of these 2 spectra. The red line is just a black body. The blue line is a fancy model. Our team theorist, Sarah Seeger, this is one of her hot models. Models by Adam Burrows show the same general behavior. What these hot extrasolar planets are supposed to have, there's supposed to be a fall off at short wavelengths due to water absorption. Here, the blue line is supposed to decrease downwards. You can see that the points certainly don't do that. If anything, they tend to trend the other direction and then jump up in this silicate resonance. Another aspect of this, we bend it in these broad bins, and you can see this is the really coarse bending of the spectrum. And the 2 points here are if we include or not include this narrow feature in the bin. And we use this to convince ourselves that this peak due to near the SIO stretching resonance is real in the data. Actually, we only claim that this difference is real. This difference here is that's a little not so significant. So it's, in a sense, it's only half significant. It's only significant if you come from the short wavelength side and go up. to show you a similar result. This is the Grillmair et al. Result. Their spectrum of HD 1897333b. They have better signal to noise because their planet has a higher contrast to the star. The star is smaller. The planet to star contrast ratio is better by about a factor of 2 or 3. Here's their data points and a similar model. I believe this is an Adam Burrows model. Again, water absorption would cause this model to trend downwards, and you can see the data don't do that. They're flat. We know that the spectra of these planets will turn down at some point beyond this because the Spitzer photometry at 4.5 microns show a much lower contrast. So somewhere this spectrum falls off the cliff towards lower values, but not in this wavelength range. So, why are we seeing no water absorption? The sort of the most naive possibility would be that the planets have no water. And we considered that for about 3 milliseconds. And the reason that we have to reject that is that it's so easy to make water. It's hard to avoid water. Oxygen is the third most abundant element in the universe. And hydrogen is certainly molecular hydrogen is very abundant in these objects. It's virtually physically impossible to make these planets without significant amounts of water vapor in their atmosphere. So they have to have some water. So the only really two explanations are that perhaps they're masked by high clouds. That would be consistent with the fact that we see a silicate emission feature. Notice that Grillmair et al. Don't see really a silicate emission feature, but the star that this planet orbits is a K dwarf, and if there are features in emission, we would expect them to be excited more when you orbit a hotter star. Our planet was a hotter star, so that's consistent. So maybe there are high clouds, and maybe they're silicate clouds that are masking the water absorption below it. There's other evidence for high clouds in the atmospheres of these high Jupiters. Another possibility is that there's some perturbation to the temperature gradient. In fact, since we see features in emission, if they're thermal features, that would require a reverse temperature gradient, a stratosphere. And in fact, it takes less than that to mask the high water. This is a result by Jonathan Fortney. It's a model in which they incorporate the effects of dynamics, that is strong circulation that is believed to occur in the hot Jupiter atmospheres, and they show you what that strong circulation, the effect that it has on the emergent spectrum. When you observe, here you are looking at the planet, here's the star. When the planet is behind the star at secondary eclipse or is opposite from you, then you're looking at the day side of the planet. And what Fortney et al. Find is that the temperature profile on the day side, the effect of the strong circulation is to make the temperature profile much more isothermal. So the spectra on the day side are much more like a black body in this spectral range. And this dip downwards due to water at 7 microns is not nearly so prominent at secondary eclipse. So in other words, when we can measure the spectra at secondary eclipse, that's when the spectra are least interesting in this respect. And that's unfortunate. But that would explain and my colleague Sarah Seeger also has other ideas on how the temperature gradient could be perturbed. She thinks that there might be, in fact, a deep stratosphere, a temperature reversal that extends to fairly high pressures. Now, I can't really articulate the physics underlying these models. In particular, I would like Jonathan, if he's online, to tell me why the strong circulation makes the temperature profile isothermal. But maybe, if he's not online, maybe one of his collaborators can explain that to me. But what I will do is I want to try to extend these a little bit, because what we're really interested in is the spectroscopy of habitable planets. And we probably can't do that with Spitzer. There are several sort of super Earth mass planets that are known to orbit close to M dwarfs. For example, Gliese 876d is a 7.5 Earth mass planet that orbits close to the M dwarf Gliese 876. And this system is 5 parsecs from Earth. And in fact, Sarah Seeger and I have a photometric program to try to measure the phase modulation of the infrared phase modulation to try to detect the planet at all photometrically, but we haven't dared to try to measure its spectrum. in order to measure the spectra of these planets, we have to go to what I regard as NASA's most important planet measuring mission, even though it's not billed that way. And this is a model of the James Webb Space Telescope. If Spitzer can measure the spectra of two bright giant planets, Spitzer is 85 centimeters in aperture. This James Webb Space Telescope is 6.5 meters in diameter, 25 square meter collecting area, runs from 0.6 to 25 microns. This telescope will have fantastic capabilities if it is even half as stable, and it's in a, it's not Earth orbiting, it's at a Lagrangian point where it should be in a thermally stable environment. You can see this model here. This is set up at Goddard, and these layers of material here are the sun shield. What I like most are these potted plants that go below it. I think these are in case there are any more budget cuts, these are the D-scope option. NASA will launch these in lieu of the sun shield. Now, we've been doing calculations of what JWST would see if we did our Spitzer investigation with JWST. For a nearby bright M dwarf, we have this IDL code that will calculate, we'll go through our analysis, and calculate the signal to noise in the planet's spectrum at a given spectral resolving power for a postulated stellar temperature. We've input here an M dwarf, which is 0.3 stellar radii, 3,500 Kelvin. We've placed a planet at 0.05 AU. The nice thing about M dwarfs is that if the planet transits, if it's in close and it transits, and it has a high transit probability, that's also where the habitable zone is. So planets transiting M dwarfs may be in the habitable zone. This planet, we've made it a super Earth mass planet, 2 Earth radii. Its temperature follows from these parameters and an assumed albedo, which in this case we assume 0.3. Its temperature is 379 Kelvin, much cooler than the planet than the giant planets I've just been talking about, and we placed it 10 parsecs from Earth. This is the signal to noise that JWST would obtain in 200 hours of observation. And you may scoff and you may think, well, we'll never get 200 hours on JWST. Oh, yes, we will. If we can measure the spectrum of a habitable planet orbiting an M dwarf, 200 hours is not out of line compared to things like the Hubble Deep Field and what our extragalactic colleagues do. So we think that in fact that the way to measure spectra of habitable, of at least some kinds of habitable Earth-like planets, is to look for planets transiting M dwarfs and to go after them with the JWST. So I'm going to end by concluding. There are two 7 to 14 micron spectra of hot Jupiters. They show evidence, both planets measured by two independent groups, show evidence for masking of their predicted water absorption, that there's evidence for silicate clouds on at least one of those planets. In either case, we need some kind of perturbations to the temperature gradient as compared to simple equilibrium models. And finally, we're looking forward to JWST taking us to the spectra of hot Earths. And I will entertain questions. And I'm sure there are lots of questions.
For the sequestering of oxygen.
Can they hear him? I'll repeat the question.
There's a mic. There's one in front of you.
Grab that microphone.
For the sequestering of oxygen in
Let me just ask people around the net if they would raise their hands on WebEx, and we'll call on them from here, but let's go ahead with the questions at Goddard.
Okay.
I recall that for brown dwarfs in the late L and early T sequence, there's a dichotomy of how you sequester, the taxonomy of those things, how cloudy they are, and so in fact that reinforces the idea of a cloud of something silicaceous material over a very hot Jupiter. But also there's evidence for carbon monoxide as well. I wondered what the arguments are against putting all the oxygen into CO as opposed to water.
Glenn's question is, why can't you just put all the oxygen into CO formation? And I think the sort of simple-minded answer is that cosmically there's more oxygen than there's carbon. So if you do that, you have oxygen left over, and that goes into water.
Okay.
If there are suggestions that there are carbon planets. If there are carbon planets where there's more carbon than oxygen, then carbon will then all the oxygen or most of it will go into CO formation and you won't have water bands. But I think carbon planets are considered exotic. So that's not the explanation that is favored.
I have a question. If I got it right, you actually, the spectra you show is the night side of the planet.
The spectra I show, the question is, are the spectra I show for the night side? The spectra were measured during secondary eclipse. Secondary eclipse, we're looking at the day side of the planet.
Okay.
So the planet's on the opposite side of the star shining directly onto the...
But I mean, the planet is behind, so you don't get the photons. The photons are being, they are being behind the star. So you get, when you get this struck from here, when it's in front of you, minus the one in the back.
We're seeing that the in eclipse and out of eclipse phase difference is very small compared to the orbit of the planet. So we're essentially looking at subtracting the same phase out of eclipse as in eclipse. So that difference is just the thermal re-emission of the photons from the planet.
If I can try that, what you're really doing at each wavelength, you measure the contrast between out of eclipse and in eclipse. It's that contrast which you show as a spectral signature at that wavelength.
That's correct.
Yeah. So
we're measuring the weight, but
the excess intensity at 7.8 microns, for example.
We're reconstructing the spectrum of the planet from the wavelength dependence of the secondary eclipse amplitude. Correct.
My question.
Okay, Goddard's still asking questions.
Drake, there's 14 planets that have been detected in eclipse.
There are 14 bright extrasolar transiting planets and some fainter ones.
What are the chances of getting spectra from the other 12 that have not been?
The two that I've shown you are by far the two brightest. So I, at least, have not proposed to use Spitzer on the fainter ones. Maybe someone else has. I think you would really be photon starved in that case, and you would require multiple eclipses to obtain spectra. JWST, on the other hand, will really do these planets really well. Come up to the table and ask the question at the table, and then maybe we should let the other notes.
You've shown the silicate emission from the planetary, potentially haze. How do you know that those silicates aren't in the disk of the system?
That's a good question. He asked, how do we know that the silicate is really associated with the planets and not associated with a disk around the star? Well, because what we see is in eclipse minus out of eclipse. That's a very short, relatively short temporal modulation. Only really a small fraction of any disk could be, if there's a lump in the disk, it would have to be very closely associated to the planet. We couldn't rule out the possibility that there's some extended dust envelope around the planet that's emitting, but you don't see that during transit. The radius of this planet during transit at infrared wavelengths is the same as in the visible. So if there's some dust around the planet, it's very low optical depth, and it would have to be very close to the planet.
Drake, I'd like to ask a question, and then we have a question at Colorado.
Okay.
The question I'd like to ask comes back to the discussion you included about the effects of the temperature gradient. Since you're looking in the thermal infrared, of course, the visibility of spectral features is going to depend upon a vertical temperature contrast in the atmosphere. You mentioned the possible effects of circulation. Could you just talk a little bit more about what you expect the vertical temperature profiles in these atmospheres to be, and how variations in that or uncertainty in your understanding of that affects your interpretation of the spectra, particularly whether or not you see a feature?
Well, you do expect, when these planets were initially discovered, my first reaction was that they probably have very hot stratospheres because they're so close to the star. We know Jupiter has a stratosphere because it has methane. Methane absorbs solar radiation, heats the atmosphere. If you put a planet in that close to the star, I would think it would have a very strong stratosphere. But when that shows how poor my intuition is, because when people actually put the opacities of water vapor and the various molecules into their codes, they found that indeed the temperature in the outer atmosphere was raised slightly, but not enough to actually invert the temperature. So the temperature profiles of these planets are not all that different from brown dwarf atmospheres, in the sense that their highest temperatures are down deep, and the external boundary temperatures are on the order of 800 Kelvin versus 1500 Kelvin deeper down. Now, maybe the observations are showing, maybe the Spitzer observations are showing us that we have more to learn there, but at least that's the current understanding.
I guess the second part of my question was, is that affecting the visibility of features? So, for example, when you don't see a feature, could it be that the thing that you're looking for is there, but the temperature contrast to enable you to see it isn't?
Yes, that's the predominant view, yes.
Okay, University of Colorado.
Hi, Drake. This is Tom Ayers. Nice talk.
Thank you.
I wanted to ask a question, actually two questions. The first one is, what are the prospects of performing this type of experiment with a large telescope from the ground, say in the infrared? And what are the prospects for doing this in the ultraviolet from space? And then the second question is that you described an alternative analysis of your own data by another group, and I wonder if you could just mention what their results were and how they differ from yours.
Okay, let's see. Let's take the first part of that question first. Can we do this from the ground? The ground-based observers are knocking on the door of planet detection. There is a tentative, like 3 sigma detection of one of the ogle transiting planets at 2 microns by Snellen. We think that the way to do this from the ground is to find a system with a bright nearby comparison star, so we can take out the effects of the Earth's atmosphere, and that would add an additional complication to the analysis, but we think it's possible. And there are proposals being submitted to try that, and we think eventually that'll be possible. The advantage, of course, doing it from the ground is that Spitzer will run out of cryogen in the spring of 2009, and also Spitzer has limited wavelength coverage. There are important features in the spectra between 2 to 5 microns where Spitzer has no wavelength, where we're not accessible to those wavelengths from Spitzer. Then the second part of the question was, what about the Swain analysis? And so I have to go back to my talk. Can you make my talk come up again?
Marco, we need the presenter ball back.
Yeah, you should be able to control it now.
As well.
Okay, go ahead.
Okay. I can't. How do I make it? Oh, up.
You should be able to do it from there. Go down to the bottom and go to full screen.
Where? Here, you do it. Okay. Whereas our analysis uses these differential eclipses, what Mark Swain's analysis, well, I guess his paper is still under review, what he does is he actually subtracts the spectra out of eclipse minus in eclipse. And we do that too, only we do that as a check on the analysis. We rely on these differential eclipses. And I would argue that you really have to rely on the differential eclipses, because if you don't do that, there can be effects in the time series that are unaccounted for in your analysis. And in fact, if you look at Mark's paper, you find that he has a term called G of T, which is the gain of the detector system, and he explicitly assumes that is wavelength independent. And let me go back a little further. This ramp is like a gain because it's due to charge trapping in the detector. When you illuminate the detector with a faint source, that is the stellar spectrum at long wavelengths, it takes a lot longer for it to ramp up to full sensitivity than it does at short wavelengths, where there is a high intensity being shown on the detector. In other words, the gain of the detector is effectively wavelength dependent, whereas Mark's analysis explicitly assumes that it is not, and that's not correct. And for that reason, I think he's probably not deriving the spectrum of the planet at all.
UV spectra.
Okay,
UV
Arizona.
spectra from space. UV spectra from space have been measured by Hubble.
Okay, Arizona
There
has
was
a question.
Far
Yes.
away.
If there were a ring around this planet, it would, of course, produce likely emission lines or emission bands, whatever one calls it, and one would distinguish that because the eclipse would be broader because of the diameter of the ring system would be broader, and therefore I'd like to know what evidence you have that in this emission that the eclipse does indeed have the breadth associated exactly with that you see of the planet continuum.
Well, at one time, rings around this planet were my favorite theory, because as you know, the planet's radius is larger than can be accounted for by simple models. One way to explain that would be perhaps a ring system, which was increasing the effective area of the planet. That beautiful theory has been contradicted by ugly facts. The transit of the planet was measured at Spitzer wave. The primary eclipse of the planet was measured at Spitzer wavelengths by Jeremy Richardson at 24 microns, and he obtains a radius for the planet in very close agreement with the visible results. So if there are rings, they have almost the same optical depth at two very, very different wavelengths, which is maybe possible, but it does argue against it somewhat. Then the other argument, that is the width of the eclipse, is that we have additional observations that we haven't published yet, and I haven't shown you, and I know that's a terrible thing to say, but add to our original discovery observations. And if the eclipse were significantly broader, the ingress to egress time were significantly different, then we would have seen that. And also Dave Charbonneau has additional data that he hasn't published yet, and he would have seen it also.
Okay, we have a question here at NAI.
You need the red light on.
Hello, this is Paul Davis at Ames. Two operational questions. One, you said you took half your data before the secondary transit and half the data during the secondary transit. Wouldn't it be better in regard to systematic errors to take a quarter before, a half during, and a quarter after?
Yeah, that's what we actually do. We start, we take a quarter before, yes. With some variation on that, depending on how quickly the telescope people can, the exact starting time. We give them a window to start.
Thank you. The other question is, you mentioned the 1 hour 0.05 arc second oscillation, and you also mentioned doing a nod in the middle of the transit measurement to get a reference. Does the nod reset the oscillation, and can you use the nod to control the oscillations, or is it better to deal with them calculationally?
The nod does not seem to reset the oscillation. Having the telescope nod is both good and bad. I want to comment about the nod. That it's good in the sense that when we see this, like this differential eclipse that I have shown you on the screen up here, that the ingress of this eclipse is actually measured with different pixels of the detector than the egress, because we're always worried that there's some rogue pixel that is causing a spurious result. So by having the telescope nod, there have to be sort of two sets of rogue pixels, and they have to conspire together to make an ingress and an egress at the right time. And at that point, you don't worry about things that bizarre. The disadvantage of the nod is that it may reset the ramp to some extent. You can see right here. There's the charge trapping in the detector. When we move the spectrum, there's a little bit of a reset of the ramp. I would like not to have that. I've since concluded that and also for reasons of comparing to Carl Grillmair, where they don't nod, that we propose to redo this to do it without the nod. That's a real subtlety of the observation.
Thank you.
Okay, there are no more hands raised. We can send it back to Goddard for any more questions at Goddard if there are any there.
Oh, Goddard always has questions.
Oh, I know.
Drake, in the spectrum, they seem to be another feature at the longer wavelengths. Is that true?
Another feature at the longer
Around
wavelengths.
12.5 microns or somewhere around there?
Well,
or some kind of structure.
But look at the error bars here. And look at the agreement or disagreement between the two different eclipses, which is what we have to go by. You can't. It's basically just scatter at the long wavelengths. And in fact, the spectra go out to 14 microns, but the Spitzer people say that there's scattered light beyond 13.2, so we don't even try beyond there. It's called the teardrop.
Okay, this is short low. Oh, that's a short high.
This is short low. This is SL2. We don't have enough photons to go to high resolution.
I have a question. Have you ever considered non-LTE effects for some of these missions? Or
have we considered non-LTE effects? If this feature is really due to a carbon-carbon stretch, which we think is kind of speculative, but if it were, then it would have to be due to fluorescence, which is non-thermal. So yeah, there could be non-thermal effects.
Yeah. Okay. Well, when I look at the spectrum, it seems to me that both Grillmair's Spectra, I think it was, and yours could be interpreted as having a double peak structure that was had a minimum near 7.6 microns and two peaks, one at higher wavelength and one at lower wavelength. Is that supportable, or is that not correct?
I mean, I think you could argue in favor of a lot of different explanations.
Yeah.
But since there are proposals to reobserve both systems, and at these wavelengths and at other wavelengths, much will be clarified after this summer. These are observable by Spitzer during the summer. So.
Which are the wavelengths?
We propose to observe it at somewhat shorter wavelengths, 5 to 8 microns, where we expect the flux to decrease, the contrast to decrease strongly. And Carl Grillmair has proposed to observe HD 189733 at many other wavelengths. I don't know the specifics.
Where would you next expect to see water?
Where would we next expect to see water? Actually, I think the best prospects for seeing water are from the ground. To detect there's a peak at 3.8 microns between water and carbon monoxide absorption that I think can be detected using ground-based observations in these planets. So that's the way I think is the real way to detect water.
Drake, could you just amplify for a second on a comment you made just a minute ago that if that feature at around just short of 8 microns is carbon-carbon stretch, it has to be fluorescence? Why is that?
Because that's the way emission from PAH molecules is seen in astrophysical sources at these wavelengths. So I guess it doesn't have to be, but I would expect that it would be in that case. Because carbon-carbon stretch would indicate PAH, and PAH is seen in many sources now by Spitzer, and it's always in emission, and it's due to fluorescence. But certainly this planet is in close enough to a hot enough star. There's enough UV to cause fluorescence.
And you have enough inverted stratospheres.
I mean, we're being speculative now, but if there are silicate clouds, those silicate grains could be associated with PAH molecules also, and they could fluoresce.
Well, but I think in this case the fluorescence is not the same as kind of fluorescence as if you had a diatomic molecule, which was pumped to a higher state and then re-radiated at different wavelength. It's really more that you might have a PAH grain or macromolecule that is flash heated by a UV photon, and then you get vibrational excitation, which is seen in emission. But the grain itself is probably slightly warmed by that UV photon.
That's exactly correct.
Yeah. It's not quite the same.
It's not quite the same, but it's still referred to as fluorescence because it's a repartitioning. It's a re-emission of the UV radiation from the star.
Well, Drake, there aren't any hands raised around the net, and so I just wanted to thank you for a really fine talk.
Thank you.
And we and thank you again, and we'll look forward to seeing you all in about 4 weeks from now. Bye-bye.
Thank you, Carl.